Right. Good evening, everyone, and welcome to this public lecture by Professor Balchandra Lakshman Rao Tembe. He is currently at IIT Dharwad. He did his PhD in chemistry, I think, theoretical and computational chemistry from this State University of New York in 1981. And then he did a postdoc from the radiation lab at University of Notre Dame, Indiana. After his postdoc, he briefly worked as a visiting assistant professor at University of Houston, Texas, and then was appointed as a lecturer at University of Hyderabad. He moved to IIT Bombay in 1986 to join as an assistant professor and worked there until 2020. 2018, I think, sorry. And since then, he has been at IIT in the Department of Chemistry at IIT Dharwad. So, unlike many other chemists we see around, he does chemistry on computers. And he will show that this could be a real fun to do chemistry on computers and how much we can learn and predict about the fundamental natures of chemical, especially the liquids. He has about 70 publications against his name and trained several PhD and postdocs. We had 2 sessions from one of his PhD students, Dr. Sonaki Keshri. We will see from his talk why he received an award for excellence in teaching being at IIT Bombay in 2002. He has held several positions. He organized the GATE as a vice chairman. Apart from GATE, he also organized the JAM exam. He has been convener of Physical Chemistry Group, head of Center for Distance Engineering Education Program. So the list is very, very long. I'm naming only some of them. So he has extensively worked on computational aspects of chemical systems. Those include liquid state theory, solvation dynamics, and charge transfer. He has also worked on understanding the physical chemistry at surfaces and interfaces. And he has also worked on understanding the mechanism of superionic conduction. So we are really lucky to have him because he is among the good teachers we can have around. And he is among the very few people who can really teach us chemistry from theoretical point of view. You will see the chemists who are mixing the solution in the laboratory, but he can really show how the same thing can be done on the computer. And they can reveal lots of mysterious things about phenomena about the chemical systems. So without taking too much of time, I'll invite Professor Tembe to deliver the lecture. Over to you, sir.
Thank you, Dr. Gaur, for your kind invitation. Can you allow sharing of the screen? So thanks again, Dr. Gaur. I have not been doing computer simulations for a long time now. I'm doing other things. So it was a great pleasure to be asked to speak to this audience. So I have tried to make it as general as possible. Computer simulations, applications for liquid structure, reactions, and phase transitions. These are really challenging things because it includes just about all that molecular dynamics can do or Monte Carlo simulations can do. And I have tried to present it here. So the outline is follows. The purpose of simulations, what are the alternatives, and what methodologies we use for simulations. Then we will go to applications such as structure of fluids and fluid mixtures, phase transitions and chemical reactions, and what are the roads ahead. So this is what we want to do. And I want the session to be very informal, raise a question, because I have tried to really cover a lot of areas so that you get a flavor of what simulations can do. So what simulations do, you will have a box containing a large number of particles. You allow them to move around by whatever method you want to use. So the standard methods are, one is Monte Carlo. We will talk a little bit about Monte Carlo because this workshop is mostly on molecular dynamics. So you will be hearing a lot about microcanonical ensemble, initial positions and velocities, how to calculate energies and forces on particles, new positions, and so on. So molecular dynamics follows basically Newton's laws or other modes of equation. And that corresponds to microcanonical ensemble, where energy is conserved, energy, number, and volume are conserved. So these are all methods of statistical mechanics. Whereas in Monte Carlo simulations, I find them a lot more powerful because you can do a canonical ensemble calculation, number, volume, and temperature fixed. And you can also do grand canonical ensembles, where the chemical potential is fixed and you can increase or decrease the number of particles. So that becomes a very powerful tool. Whereas in molecular dynamics, you cannot really add or subtract particles because it's going to be very difficult, because your entire force equations will change in the middle of the sequence. So I will try to spend some time on Monte Carlo simulations, and then we will go ahead to different applications. So the basis for all this molecular dynamics or Monte Carlo are intermolecular forces. So there are different kinds of them. You all know about Coulombic forces, dipole-dipole interactions, ion-induced dipole, dipole-induced dipole, forces between neutral molecules, that is your standard universal van der Waals forces, and electron repulsions between electron clouds. Usually we use the R-9 or R-10 potential, although the real potential is exponential because quantum mechanics tells you what are the repulsive forces between atoms. But these are very convenient for calculations. R-12 is very standard in your Lennard-Jones potential. So if you know R-6, you can get R-12. So computations become very, very easy. So the computer simulations have become extremely powerful because they are fairly simple to do. Whereas if you go to the theory of liquids, you have to go to the configuration integral and calculate the distribution functions. Of course, molecular dynamics and Monte Carlo also give you distribution functions, but the theories give you different ways to calculate the distribution functions, whether it's an integral equation method or a density function method. So lots of approaches are there. The progress has been, I would say, a little slow because molecular liquids are very difficult to handle using theory. Molecular liquids are very difficult, whereas computer simulations, it is very, very easy to take any molecules on your screen and go ahead and simulate what you want. So what is done in all your simulations, you have a set of molecules, you have a central particle. Around that central particle, there will be a cluster of other molecules. We call it the first shell, second shell, and so on. The chemists usually like shell structure around atoms and molecules. So what happens in a simulation, you start with a direct potential. Direct potential is the potential between particles, such as a repulsive force. I have shown here a repulsive force. The force repulsion becomes infinite when the molecules are very near, and it is zero when you're outside. So you start with a potential, either a repulsive potential or something like a Lennard-Jones. Look at this, the black one, it's a Lennard-Jones potential. And as the result of the calculation, you calculate either a configuration integral, which is very difficult to calculate because you cannot integrate over infinite degrees of freedom. So a better option would be to do two integrations less. So your pair distribution function is really, you have your interaction potential divided by kT. This is your Boltzmann factor. And you integrate over all variables other than 1 and 2. So that gives your distribution functions. So this is really like a reduced, you have a configuration integral which is difficult to calculate. You reduce it so that you can really estimate your pair distribution function. So whether you do Monte Carlo or molecular dynamics, both of them allow you to calculate these distribution functions. And from these distribution functions, you can get thermodynamics very, very readily. Whereas when you do molecular dynamics, you can calculate dipole-dipole time correlation functions. These, I think, in this studies, you will study how to calculate these correlation functions. And once you know the dipole-dipole correlation function, its Fourier transform gives you the spectrum. So really, the structure of liquids can be studied through your pair distribution functions, and the dynamics can be studied through your dipole-dipole time correlation functions. So the goal of simulations is to give you these correlation functions as accurately as possible based on the potential model. And then you can do either your thermodynamics or different kinds of analysis. So I will briefly spend, so this is how you calculate the radial distribution function, G of R. Its physical meaning is local density divided by bulk density. So you will see in this diagram. So I have a central particle. Around that central particle, I construct some shell, this dotted line, there is a shell here. So in this shell, there will be many, many molecules. So that I call as the local density in that shell. And if I divide that local density by bulk density, I get the pair distribution functions. So you will see that as the shells go further and further away, the influence of the initial particle is very small. So the ratio of the local density by bulk density will be 1. So my G of R goes to 1. So that is what this diagram shows. So every point is a ratio of local density by bulk density. So you see that as I go far away, that ratio becomes 1. So the structure, influence of structure is very, very small. Whereas I go very near the original particle, the influence is very strong. So this is really your pair distribution function. So for most liquids, that structure effect of the original particle is very small as I go far away. So that becomes unity. Whereas I do simulations on solids, it will really never go to 1 because there are always fluctuations in solids. So if you have a lattice, I go very far from that original point, there are still fluctuations. So solid state simulations are a little harder than liquid because of this lack of uniformity. And it is also important for solids that my potential I have to take into account up to large distances. So now we'll quickly discuss Monte Carlo because I don't know whether in this workshop you are doing Monte Carlo, but I think that is important because the scope of Monte Carlo, I think, extends simulation techniques to study phase transitions as well as reactions, inserts of particles. So although I have not personally used this grand canonical Monte Carlo, I think it is about time that we learn about it. So what is done in Monte Carlo is that you have a configuration, and from each starting configuration, you go to new configuration, say step 1, step 2, step 3. So in each move, I move particles, and when I move the particles, the potential energy naturally changes. So before I move the particles, I calculate the old potential energy, which is the energy of the old configuration. After I move the particles, so these are my new positions. So I have a new potential energy that is after the move and old potential energy before the move. So the algorithm is very simple. If the new potential is less than the old, the new configuration is lower in energy than the old. So the Boltzmann distribution says that the lower energy, the lower the energy, higher the probability. So I accept any move where the new potential is less than the old potential. Whereas if the new potential is higher than the old potential, normal sense may say that reject it, but no, you do not reject it. Accept it with this probability. Accept it with a Boltzmann probability. So this was the great thing that Metropolis and Teller and others did in 1953. So it opened up an entire new way of doing simulations. So what is done here? So there is an old configuration and a new configuration. I calculate my delta V, which is the change in the potential. So look, this diagram explains all about the Monte Carlo. So if the new potential is less than the old, my delta V will be negative. So if delta V is negative, so e to the minus delta V will be positive. So I am in the left of 0. So whenever e to the minus delta V is greater than 1, surely I will accept all the moves. So as I do the simulations, every move that is lower in potential from the original one will be accepted. Whereas if the new potential is higher, you compare that e to the minus delta V with a random number. Now, if that random number is less than this particular curve at each point, for each delta V, I compare e to the minus delta V with a random number. If the random number is less, I accept the move. If the random number is more, I reject the move. So this allows me to generate a large number of samples. It allows me basically to generate the entire canonical ensemble. It allows me to generate the canonical ensemble. So that is how I do Monte Carlo simulations. So the next one now I want to comment, because I do not know whether you will have an opportunity in this workshop. In the grand canonical, what one can do is I can either insert or delete a particle. So that is the beauty here. So that allows me to study phase transitions, because whenever there is a liquid vapor equilibrium, particles will be moving from liquid to vapor and vapor to liquid. So I should have a mechanism to insert particles. So again, these are governed by the grand canonical probability density. So if you have not already studied it, it's just a very simple formula. The probability distribution for a given set of particles in the grand canonical probability distribution is given by this formula. Lambda is a de Broglie wavelength. N factorial is to take into account the indistinguishability. E to the beta mu n, mu is our chemical potential. So you will see that in the grand canonical ensemble, in addition to your potential energy, the chemical potential also plays a role. Chemical potential also plays a role. So when you want to insert a particle, that is you want to go from n to n plus 1, the probability for that move is 1 by 2 into 1 by v. That is to insert a particle. Whereas when you delete a particle, n plus 1 to n, so it is half of 1 by n plus 1. So these are all following directly from your grand ensemble probability density. So then the acceptance probability to go from n to n plus 1 turns out to have this formula. It depends on the chemical potential as well as the difference in the potential energy. In the canonical, we just had the second term. Now your e to the beta mu also plays a role. So by doing the simulations for different potential, you can simulate two phases at a given time, because we know that whenever there is a phase equilibrium, two phases are in equilibrium. So two phases will have the same chemical potential, but they will have a different density. So when I go to phase transitions, I will use this particular formula. So this is to go from n to n plus 1. Now similarly, to go from n to n minus, yeah. Any question? So to go from n to n minus 1, this is the formula. So earlier you see that you had a e to the plus beta mu. Now here n minus 1 and n have been changed. So you can use this and generate a large number of configurations where you insert particles, you delete particles. So we will come to this when we use particle insertions and phase transitions. So now what I will do, so since I have discussed some theoretical methods, so I will be commenting on several problems. I will talk of alkali and alkaline earth halides in solution, because this is my favorite area of work. Then we will also talk of mixed solvents and preferential solvation. Then we will also talk of movement of ion pairs from one configuration to another. Now that once you set your configuration, you can do many things using simulations. So that's what I will discuss. Some examples and some, as Dr. Gaur mentioned, we can get many interesting results by doing very simple simulations. So that would be my goal. So some of the first work we did was to study the ion pair association. That is, sodium chloride is the most well-known ion pair. So I want to study what is the potential of mean force between sodium and chloride. So we use a method where I fix sodium and chloride at a given distance and calculate the fluctuations in the force between sodium and chloride. So this delta F RT is the difference in force between chloride ion and the sodium ion. So if I take that difference, which is delta F, okay, so my actual force will be direct force between this and the fluctuating force. So when I average this and integrate, what I get is the potential of mean force. This is a very standard formula. So if I want to know the potential of mean force at any given distance, I want to know the potential of mean force at a large distance. So suppose I am very far away between the two, then I can say that at a large distance, the potential energy between this is just your Q1 into Q2 divided by dielectric constant times R0. So at a large distance, I can assume that it's a dielectric medium and the potential is just Q1, Q2 divided by epsilon naught R. Whereas at a small distance, I really don't know the dielectric constant, because dielectric constant is a macroscopic property. For small distances, I calculate the fluctuating force and I integrate to get the potential of mean force. Okay. So this is the same thing indicated in a larger perspective. These are my sodium and chloride. I fix them at different distances. solvents are fluctuating. I calculate the fluctuating force, then I average the fluctuating force, and when I integrate, I get what is called the potential of mean force. And potential of mean force is nothing but it's related to the pair distribution function. It's related to the pair distribution function. Minus KT log GR is nothing but the potential of mean force. So now let us see some very, very interesting results. If I put sodium chloride in water, and calculate the potential of mean force, what it shows is that there is a contact, there is a one minimum here, then there is a second minimum, and then the whole thing goes to zero. This is basically the structure of water on the association between sodium chloride. Okay, so the first observation is that in water, since it is a very high dielectric constant, the moment you add them in water, this is the direct gas phase potential between sodium and chloride. The moment you put it in a dielectric constant, which is almost like 80, the interaction potential suddenly becomes very, very small. And not only you have a contact ion pair, you also have a solvent separated ion pair. That is the effect of solvent on your association. So this is red one is in water, whereas the green one is in DMSO. We were also interested in DMSO because in chemistry, people use water as a solvent. And whenever you cannot use water, they will use non-aqueous solvent. DMSO is because many things dissolve in DMSO. They may not dissolve in water. Many organic molecules will dissolve in DMSO, so you can do reactions. So you will see that the first difference is in DMSO, the contact ion pair is very, very strong, whereas a solvent assisted ion pair is very, very far away because of the size of DMSO. Now, if you see the difference between this minimum and this minimum, it roughly corresponds to one water molecule inserted between the two. Whereas if you see the difference between this around say almost 3 angstroms to 7 angstrom, the DMSO molecule is almost 5 angstrom in diameter. So let us see some pictures here. So the way I will study ion association now through different ion pairs.
So sorry to interrupt you, sir.
Yeah.
From the previous picture.
Yeah.
So can we conclude that water is a better solvent for NaCl?
No, it's better in the sense those who are not hydrophobic, they will dissolve in water. All those solvents which love water, they will dissolve in water. Whereas something like if you say methane will not dissolve in water. Whereas methane will dissolve in DMSO. Neopentane will dissolve in DMSO because it's a like association. DMSO has 2 big methyl groups. Your methane will go there. It's very happy to be in DMSO. So a lot of non-aqueous chemistry is done in things like DMSO, ether. Acetone also is better because it has that CH3 group. So it is the hydrophobic effect. So what water does, if you put an object which doesn't like water, they will all be associated with each other and they will repel water. So that's called hydrophobic association. So that's what protein molecules also do. Whichever part of the molecule doesn't like water, it will go away from water. They form like, you must have seen micelles, no? You must have heard of micelles.
Right.
So, micelles are objects where they aggregate because they don't like water.
Yeah,
so there will be a structure inside the micelles, same as your cell wall. Your cell wall consists of fatty molecules. Okay? Cell walls, they consist of bilayer of fatty molecules. Some water will go in, but it will avoid water as much as possible.
Right. Thank you.
So this is your contact ion pair. This is a solvent assisted ion pair. Okay. And whereas this is a solvent separated ion pair. See, there is one solvent which is separating the plus and minus. So since we did this calculation in water and DMSO separately, now I want to do the calculation in a mixture of the solvent. So that, see, chemists are also interested in mixed solvents. So when you do that simulation, you can also see, suppose this is my sodium and this is my chloride. Okay. In this case, it is a sodium. So you may expect from a physics point of view that the 2 plus ions will not come near each other. But in reality, it is not like that. When 2 plus ions are near each other, the oxygen of DMSO can converge around it. So plus, minus, plus. So the solvent sites help positive ions to come together. The negative solvent sites, which are all around here, you see, these are the negative solvent sites. They allow even plus ions to come very near each other. And that is how in chemistry, there are many reactions people do in solution. reactions between ferrous and ferric, cobalt and nickel. These are all very highly charged ions. Bivalent and trivalent ions, they can all come together because of the solvent, making the plus ions also come together. So this is how you study the distribution, density profiles of your solvent around your ion pairs. And so why we got interested, now you see this picture here, there is a strong contact ion pair everywhere. But when you go to a mixture, you will see that the contact ion pair has completely disappeared. The contact ion pair has completely disappeared because the solvent mixture, there is a lot of competition between water and DMSO to get in between the ion pair. So it doesn't stabilize the ion pair at all. It doesn't stabilize the contact ion pair at all. So it at most stabilizes a 5 angstrom solvent shared ion pair and a second ion pair at a larger distance. It has minima far away from the contact. See, earlier that was all contact. So many contact ion pairs here. So in a mixture, contact ion pairs were completely absent. So now these are all done by the force biased molecular dynamics. So let us say that I want to prove whether this is correct or not. Then what I do, I start the simulation at some midpoint, okay, and see, suppose this is called a transition. So I have one minimum here, second minimum here. Suppose I start the simulation at this midpoint, either it will go to the left or to the right. So I can, by the number of times it goes to the left and to the right, I can find out the depth of these minimum. So that is what this shows. Now what I am doing in these simulations, I start my simulation at the midpoint and see whether it goes to the left as well as right. That allows me to say whether it's a genuine local maximum and a genuine minimum. So you will see that when I start at one minimum, it fluctuates and remains in the same minimum. Whereas when I do one more simulation from one ion pair, it fluctuates and goes to the second one. When I start from the second ion pair, which is far away, I do the simulation, it comes to the inside. And when you start at 7 angstroms, it oscillates and again goes back to 7. It shows that both these minima are really real minima because I have transition. I can go from this point to either side. So you know that molecular dynamics is a reversible. When you change T to minus T in molecular dynamics, in principle, you should recover the initial configuration. That is one of the requirements of molecular dynamics, although it doesn't happen in reality. So these are all called trajectory calculations starting at the maxima. It allows you to go from one ion pair to another. So this is one kind of work. So this I will skip. Now, whatever I said, I will represent once again. A contact ion pair will be something like that. Okay. So this is my contact ion pair, no solvent in between. So now this I call a solvent assisted ion pair because you saw that between two sodium ions, there was strong interaction between sodium and sodium because the negative part of the DMSO will make even plus come to each other. So that will be whenever you find plus ion pair, the solvent is assisting ion pairing. Here it is a solvent shared ion pair, whereas this is now a solvent separated ion pair. See, each of the configuration, each of the surrounding between the ion, it's all completely surrounded by the solvent. So this is a solvent separated ion pair, where this is solvent shared ion pair because the solvation shell of each one is not complete. So this is partial solvation, but this is complete solvation. So we can study several ion pairs now. So I will just give one example. So not only we can study ion association, you can also study entropy of solvation, enthalpy of solvation, hydrogen bonding, all these things you can study. And that is the power of your simulations. It allows you so much detail that you don't know how much to put in the paper and how much to reject in the paper. So much detail is there. So you will see that most papers on simulation, they have more on supplementary data than the main paper because so much additional information is there. Okay. So now you can also study several other properties. I will not. So what I want to do now, I will just go to another example. Suppose I have a calcium chloride ion pair rather than a sodium chloride. The difference between calcium chloride and sodium chloride will be around each calcium, there will be 2 chloride ions because it is CaCl2. The valency is such that it's a divalent ion. So it will need 2 chloride molecules to complete the valency. So you need to do several simulations here. When you do simulations like that, so here we took water acetone mixtures because people use a lot of water is an aqueous solvent, whereas acetone will also allow non-aqueous objects to be dissolved. Okay, so acetone is a good solvent for many organic reactions. So mixed solvent they use for good yields. So when you do calculations like that, there will be two sets of calculations. When the second chloride, see you have, when I have calcium chloride, there will be two chlorides. In the solvation shell itself, the second chloride can be here. So I have Ca2 plus Cl minus and a second Cl minus. So I need two sets of simulations where the second chloride is inside or the second chloride is outside. So the main point to see in these graphs is that whether the second chloride is inside or outside, the graphs are looking very similar, you see. So this is chlorine inside, chlorine outside. They look pretty similar. Okay. Chlorine inside, chlorine outside, they look similar. So whether I have a single negative ion in the shell or no single ion, because water itself is taking the place of a Cl minus. So water is a strong dipole. So you don't see much difference between a chloride in and a chloride out. So this also shows that I can do simulations when several negative ions are present for a single cation. These are little harder simulations, but so you can do that. So again, now how do I know that a contact ion pair is there or a solvent separated ion pair? So I can do repeat exactly. These are all trajectories, and the trajectories will tell me how long the ion pair resides in the contact ion pair, which is 3 angstroms, and the solvent separated, which is 5 angstroms. So I can verify my potentials of mean force, which are really representatives of distribution function, through these residence times calculations. Then I can also do the running coordination number. Running coordination number tells me as I go further away from the plus ion, there will be a second shell, there will be a third shell. So as I go from the central ion far away, the number of solvents will go on increasing. So running coordination number tells me as I go from 0 fraction of acetone to 100% of acetone. So you will see the running coordination number goes from this to the largest value. This is in the pure solvent. This is when no acetone is present. So whereas when there is no acetone present, you will see that the running coordination number of water is very high. So it's a mixed calculation. 0% represent 100% water. 1 represent 100% acetone. You see that when you go from 0 to 100%, so it goes in this way. So most of the time, you will see that when you have a mixed solvent, most of the time it is dominated by water. So when you have mixed solvents, you will see that almost up to 80% of acetone, it is mostly water that is present in the solvation shell. And it's only when you go from 80% to 100%, lot of acetone starts coming. So whenever you have mixed solvents, there is usually a domination of water. In these cases, water dominates because it is small in size, number one, and the oxygen site of water, whose charge is almost around minus 0.8 to minus 0.9. Since it is very strong negative charge, it comes very close to your positive ions. So all positive ions will be very strongly coordinated by water. Okay, so this is what we find. So you can do similar, just as you do for a positive ion, you can also do for a negative ion. So you can continue this. So let us not go into all these details. So then the other thing, so here I am showing as I go from this divalent case to these studies, we can also do our studies in supercritical fluids. So you know that supercritical fluids are fluids which are above the critical point. So in case of water, the critical point is 647 degrees Kelvin. So when you, now why this interest in supercritical point? Because chemical engineers are very strongly interested in supercritical extractions. Whatever you cannot do at room temperature, in a supercritical temperature, things which do not dissolve at a normal temperature become soluble in supercritical water. So supercritical extraction is a very powerful industrial method to extract different objects. So the purpose of these slides is merely to show the difference between a supercritical fluid and a normal fluid. See the the lower one is a normal fluid, ambient conditions. You will see that in ambient conditions, you have a strong presence of a contact ion pair, and you have a strong presence of solvent separated, solvent shared ion pairs, as well as solvent separated ion pairs. You will see that 1 minimum, 2 minimum, and almost a third minimum. Whereas a supercritical fluid, the dielectric constant is very, very small in a supercritical fluid. So you will see that here in ambient conditions, the dielectric constants are large. So you will see that the potential of mean force are almost minus 15 to minus 30. The dielectric constant has reduced the potential of mean force significantly. Whereas when you go to a supercritical fluid, the dielectric constant is small. So the interactions become stronger and stronger. The solvent influence is less. So it is predominantly dominated by your contact ion pair and not by your other ion pairs. All these minima are not even a local minima. So when you do this trajectory calculations, you will see that in ambient conditions, you have contact ion pair, solvent shared ion pair, as well as a solvent separated ion pair, whereas the supercritical very strongly dominated by the contact ion pair and hardly anything beyond. So this slide is to show that you can do simulations not only in your normal liquids, you can do in supercritical liquids. Okay, so that is this point. So next we will show one more result. This is again a rather interesting result. These fullerols, you must have all heard about this Buckminster fullerene. C60 is your fullerene molecule. This doesn't dissolve very much in water. Whereas when you substitute some sites on fullerene by OH groups, so it's called, these are like alcohols now. So these 2 OH groups on this fullerene, 4 OH groups, 8 OH groups, 12 OH groups. So all these have been studied. All these have been studied. And the main reason to study these things is that these molecules can be drug carriers. Suppose this cage is a little bigger, I can put a drug molecule or some ion, something inside, and it can carry from place to place. So these studies became very crucial because people were interested in carriers. So now whatever we did for ions, we want to do for these fullerene molecules. So that is what the next slide will show. So if you just do fullerene, suppose, so we want to know fullerenes as well as fullerols. So again, I will have a contact ion pair. You will see that 2 fullerenes are near each other, solvent shared or solvent assisted, and the solvent separated. So I can get microscopic pictures of the solvation around these moieties, and let us try to interpret what these things do. That is the goal here. So one sees that if I go from fullerol, the black line is a fullerol line. As I keep on adding OH groups, so what this is doing, it is lowering the contact ion pair. Okay, and it is making the whole thing shallow, because now instead of just a hydrophobic water repelling thing, we have water attracting objects here. So they will associate with each other and make the potential of mean force lower and lower. So you will see that what the association of OH has done is that it lowers the contact ion pair and it makes the entire thing much shallower than a water repelling C60. So that is what we learned from here. These are some solvent structures around it. And also we can calculate. So these are some details, how the minima change as you change OH groups. Okay. These are again residence times. You will see that C60 is strongly located here. Then as I go from C60 to other molecules, you see the black one is inside because it is the sharpest, it is the least sharp minimum, whereas the green one is highest because it is strongly bounded. So this potential of mean force will be minimum, so the residence time will be maximum. That's what it does. Now, the other interesting thing now here is that if I go from C60 to C60 OH12, okay, in my solvation shell, the number of water molecules also changes. Okay, you will see that if I go to C60 OH twice, okay, these are my first shells, these are my second shell. It tells me how the running coordination number change as I go from a completely hydrophobic to hydrophilic. So we can also calculate diffusion constant using green Kubo formula. You will see that C60, since it is water repelling, it moves a lot in the solution. Okay, the diffusion constants are very large. Whereas when I have molecule like C60 OH12, it is very strongly bounded to the solvent molecule, so the diffusion constant decreases. So there is one result which again can be easily compared with experiment. And this is probably the most important. So you will see that when I have a C60 which does not like water, the free energy of solvation is positive. So whenever delta G is positive, it is not a favorable process. Whereas whenever the free energy is negative, So the process is favorable. So you will see that as I keep on substituting OH molecules, as I keep on substituting OH sites on C60, the free energy goes on decreasing. So you will see that the C60 OH12 is most strongly liked by water, and the free energy of hydration is most negative. So we can even study the solubility studies using this molecular dynamic simulation. That is the main message here. That is the main message. So it talks of diffusivity, it talks of the depth here. Okay, it also talks as the number of hydroxyl group increases, how the diffusion constant decreases. All this is contained here, and this is my free energy of solvation. You will see that as you go from C60 to C60 OH12, the solubility increases and the free energy of hydration is decreasing strongly. Now, next thing, these are again osmolites. I won't want to go too much into that. So osmolites are those objects when you add in a protein solution, it can salt out those proteins. Salting out is really you have a protein solution and you add these urea or other osmolites, it will precipitate the protein out, coagulation process. I will not discuss this too much. So let us go to this. I find it very fascinating. We all know the phase diagram of water. So that is above the critical point, you will have only one fluid phase. So that is one thing. Then this is your normal boiling point of water, 100 degrees. So this is your critical point, 373 plus 273, that is about 640 K. This is your triple point, and you have phase equilibrium here. So the question now to ask is, can water models produce this phase diagram? Can water models produce these phase diagrams? So we go now from a simple question of either a supercritical solution or a normal solution which does not study phase transitions to the critical point and the triple point. So it is quite reassuring that the computer simulation have reached such a stage that I can even predict the phase diagram using an intermolecular potential. So that is what is here. This is now this is the study of triple point that is in this region. So water not only has a triple point, it has several phases. One type of ice, okay, another type of ice. It has some 12 different types of ice. It has a liquid, okay, it has a vapor. This is a low density and high density. So they are able to predict this entire phase diagram using models of water. To me, this seems to be one of the best results of simulations, that I can predict the phase diagram of water. Not only that, you know that for water, 4 degrees the highest density in water. If you go either side of 4 degrees Celsius, okay, 4 degrees the most dense water. In fact, ice floats on water because 4 degree water is denser, so therefore ice will float in water. So that also has been studied with different models. So these for the triple point. Now I want to go to the, so these are some of the predictions now. See, these are all the predictions of different models, okay. Triple points predicted by different models of water. We will not go into that. You will see that some of them do not predict very well. Some of them predict very well. So that is not our concern here. The main success is that using models of water, I can predict triple point. Now I want to go to the some water models. I just want to comment. So these models are A, B, C are planar models, whereas D is a tetrahedral model. These are different models of water, okay. So now you can have a water model with 3 sites, 4 sites, and 5 sites. Okay, this is called a 3-point model, 4-point model, 5-point model. So these are all their models. So what is the purpose of this? Which model gives me the best critical point now? We are going to study the critical points. So this is just to illustrate 2 different models of water. So tip 5P will have 5-point charges, whereas this model is slightly different. So many models are there, ST1, ST2, MCY. These were all in 1970s. So this came in 80s, 90s. Now these are 2000, 2010 improvement in model. So why do we need an improvement in model? Whether it can give me better prediction and comparison with the experiment. So what we do, I will briefly describe how to calculate the phase diagram now. In the grand canonical Monte Carlo simulations, I take 2 cells now, 2 cells. Each one will be your vapor and one will be your liquid. So I keep on moving molecules from one cell to another at the same chemical potential. at the same chemical potential. So I do this simulation. So with this simulation, I can now construct a phase diagram. So what they have done now, each move consists of either displacement of molecules, rotation, or molecular exchange. You can exchange molecules between these two cells. So do those simulations. So again, you have to do either 1 lakh or 1 million configurations for equilibration, then again for data collection. These are all grand canonical. So when you do that, this is what is the result. This is what is the result. This is a low density region. This is a low density region. Okay. And this is a high density region. So I construct these points for different chemical potential is the same. So I will have two different densities corresponding to the same chemical potential and the same temperature. So I construct these. Now these are for different models. This is a 4-point model. This is a 3-point model. This is a DANG model. This is a TIP 5P model. So these are all graphs plotted for your different models. Now, how do I construct the critical point? How do I get the critical point from these calculations? So these are your standard scaling laws. Since most of you are physicists, you would have studied stat-mech and phase transitions. So difference in density is plotted as a parametric equation between critical temperature and actual temperature. A is some parameter. So similarly, this is one scaling law. This is another scaling law. Suppose A and B are known. So I can now find the critical density and the critical temperature by fitting everything into this equation. So fitting my data of phase diagram into your scaling laws, I can predict now. Okay. So critical temperature for TIP 5P water, 546 Kelvin, DANG Chang 590, SPCE 635, and experimentally 647. So to me, the greatest success is that using these models and simulations, I can even predict a critical point to such. I mean, I'm not saying it is fantastic, but if I can come within 20 to 30 degrees of the critical point using a simple model, I think it's a great success. Some of you who studied icing models, you know that even to show the existence of a critical point, it took an extraordinarily difficult calculation for the two-dimensional icing model. So to know that using simple parametric model potentials, I am able to get the critical point of something like water. To me, this is a great success. So similarly, to do the phase diagram, triple point, that is another great success. So now I want to study a chemical reaction now. So I had said in my title that we want to study chemical reactions as well. So how do we study this chemical reaction? So in this chemical reaction, I have a molecule CH3Cl. It's called methyl chloride. One Cl comes from the left side. One comes from the left side. It attaches to the carbon and the second chloride goes away. That is my reaction. So this is called an SN2 reaction because nucleophilic displacement. So what happens here? This is a tetrahedral molecule, CH3Cl. So imagine a tetrahedron. I don't know. Can you see these three fingers here? So if I bring one chloride, from this side, the triangle will flip. See, the triangle will become planar and it will flip so that one chloride comes from this side and the other chloride goes away. So you will see that one chloride comes to this tetrahedron, the three faces. This one goes away. So there is an inversion of configuration. So this is a tetrahedron. So the transition state is a trigonal bipyramid. So what is a trigonal bipyramid? In the center, I will have a triangle. On both sides, I will have chlorides. So one chloride will come from the left and one will go to the right. So this is called an inversion. The configuration is inverted. The configuration is inverted. So now how do we study this? The way we study, again, remember we talked of a force bias molecular dynamics when I studied forces earlier. What I do, I have my CH3, Cl and Cl minus at this distance. So let us say that this is my distance. I add this potential between this Cl minus and CH3. I insert this extra potential. So what this potential will do, it will make sure that Cl prime and CH3Cl remain in this range of distance. This is a bias potential. Then I take that distance to be something different. I take a different distance, insert that bias potential, do a simulation. So keep on doing a large number of simulations where I cover the distances from the reactant to the product. I cover the entire ranges of reaction using this bias potential. Okay. These are also called umbrella sampling. So these are like umbrellas now. So these are very standard in your Monte Carlo simulations. So what is the result of this? So I want to show this result. When you do the reaction in the gas phase, I bring the Cl minus to this CH3Cl. So when you bring this together, since that carbon has 5 coordinates around it, it's a repulsive situation. So the entire potential goes up when this chloride comes here. Only when the second chloride goes away, the potential becomes small again. So that is what this is showing. When the chloride minus attacks this CH3Cl from the left, I go here at the transition state. At the 0 point, both chlorines are near the CH3. So it's a very high energy state. This is a transition state. And when the second chloride goes away, again I have a situation like a reactant. So in this case, the reactants and products are the same, except the configurations are different. In one case, Cl minus is to the left. In another case, Cl minus is to the right. So this is in the gas phase. When I put them in the solution, you will see that the barrier height has decreased tremendously. And not only that, 2 minima have appeared in this potential. This is the gas phase result. I reverse my argument. This is my gas phase result. Okay. There are 2 minima in the gas phase because when this Cl comes very near this CH3Cl minus, there is an ion dipole interaction. That ion dipole interaction gives you this stability here. 2 minima in the gas phase. Whereas when I put in the solution, to remove that Cl in the solution, I have to do a lot more work. Because I have to disrupt the solvation shell. In the solution already, there are a lot of water molecules around. So this Cl minus to come and attack, it has to remove all the water molecules around it. So the barrier is much higher. So the barrier here is the difference is 28 kilocalories per mole, and the calculations and experiment match completely. So this is the first case where one could study a displacement reaction through Monte Carlo simulations. I generate the potential. This is the gas phase potential, entirely quantum mechanical. This is a liquid state potential, entirely classical. Okay. So you see that we can predict the potential energy barriers in solution to such a good accuracy. 10% accuracy is generally fantastic. So this is another kind of reaction I can study. I have a chain molecule here, another chain molecule. If I put a double bond in this chain molecule, how does my end-to-end distance change? So I can study that. I can study the correlation function between site 7 and site 12. So you will see that whenever an extra double bond is inserted, the relaxation time or the distance that decreases very slowly compared to this chain, which is saturated. Saturated chains where all bonds are free to move, whereas unsaturated chain, there are double bonds. So the moment I insert double bonds, the flexibility is reduced. So the relaxation is much slower. So these can be studied. So, and another reaction we studied for a long time. So this is a very famous reaction known since 1952. We studied it almost for 40 years. We have not got a final result yet. I will also comment why we cannot get. So these are molecules where this X on this side is called an exo, whereas this X below is called an endo. Okay. So what people found is that exo dissociation is faster 1,000 times than the endo dissociation. This endo means inside. So you have this molecule here. One X is inside, so it's called an endo, whereas this exo. So people have found for years and years that exo dissociation is much faster than endo. So we tried to do many calculations, almost 30 to 40 years. So if some dissociation is faster, the potential energy should be lower. No, whenever the potential energy is lower, the reaction will be faster. That is a standard Arrhenius kind of a thing. But we have never found an answer to this. We have found that exo and endo dissociations are not very different when you do molecular dynamic simulations. The reason is when we do exo and endo dissociation, the molecule is held rigid. So when the molecule is held rigid, that rigidity in real reactions, the molecules also vibrate. So even a 0.1 angstrom change can give you 10 to 20 kilocalories per mole difference. So it is an internal structure in classical molecular dynamics. We are not able to account for the internal structure. So therefore, we have to go beyond classical molecular dynamics. So that is what now it is the next one. Before I conclude, I will say this is a new technique now. They have started doing this ab initio molecular dynamics. So what they are doing here, it's a finite temperature dynamical trajectory. It uses using electronic structure. It combines your Schrodinger equation calculations along with your molecular dynamics. So what they do, the rate of change of positions will be derivative of your energy, which now depends on the wave function as well as the coordinates. So they will calculate a full Born-Oppenheimer type of a calculation, calculate how the positions of nuclei move will be governed by this, whereas how the electronic wave function changes, that will be governed by this equation with a parameter mu and Lagrange multipliers. So they have done these calculations. These are called ab initio molecular dynamics. They are far more expensive than your normal molecular dynamics. So I do not know whether in the workshop they are going to disclose ab initio molecular dynamics. It's also called Carr-Parinello. These are new techniques. So what are the advantages of new techniques? I can have these molecules get absorbed on a silicon surface in the presence of water. So I can study how the molecule gets absorbed, whether it forms a dimer, whether it forms an additive product. So many reactions can be studied. And this ab initio molecular dynamics is 20 to 30 years old. So with the increase in computer power, I expect these to become far more powerful. And not only that, I can study the spectra. So one example here, there is a spectrum of HCl. So I can study the spectrum of HCl in the presence of water. So these are all different spectra. So through the dipole correlation functions using ab initio molecular dynamics, I can even study the spectra of solutions like HCl or H2F2. These are solution spectra. They can be calculated using ab initio molecular dynamics, and you can compare with experiments. A lot of scope is there, but of course, these are very expensive calculations. You will see that it's only HCl. We are still 2022. We still have diatomic molecules in solution. Suppose I want to study a complicated molecule, that is a long way, but maybe new computational methods will come, new techniques will come. Parallel algorithms are already there, so you may be able to do much better. So let me conclude. So my first conclusion is that simulations can provide very interesting answers and predict a large number of chemical and biological processes that are accessible to simulations. The real challenge even today is to find a good model potential. You will see that even for a molecule like water, you have at least 10 models of water. Some models give the triple point very well. Some models give the critical point very well. So whether a single model will give you the entire phase diagram, that is still a question, but it really doesn't matter. If some model is very good at high temperature, I will use that. If some model is good at low temperature, I will use that. Ultimately, my aim is to really solve engineering problems using these modeling. So chemical engineers are probably doing more molecular dynamics than chemists nowadays. And the other comment is that even structure of solutions, phase transitions, chemical and biological reaction, they can also be studied fruitfully using molecular dynamics. It's a very powerful tool. You don't have to know too much statistical mechanics. In fact, a lot of biologists do a lot of molecular dynamics. They need not know the word ensemble. They just use a package and give you a result and say this protein will fold in 70 microseconds. This protein will fold in 300 nanoseconds. So people can study a lot of physics and chemistry and biology using this simulation. They are very powerful. So that is the message here. A lot of options are open. So these are some references. Alan and Tilste, I'm sure you will be referring to this book in your workshop, very well-known book. And those who want to study statistical mechanics, Hansen and McDonald's, a wonderful book. Lots of theories you can study. Then this is a triple point coexistence curve, vapor-liquid transition, reactions, and some of our papers. Okay, so thanks again, Dr. Gaur, for asking me to speak after many years, and I will be happy to discuss any questions that you have. Thank you.
Thank you, sir. Thanks a lot for giving us the overview. What can be done using these computational techniques? You also give us an idea that we can, apart from the molecular dynamics, we can use Monte Carlo and ab initio molecular dynamics. So those are the things which we are not planning to cover in this workshop. But now,
at least I thought they should hear them at least so that they know the scope and
yeah,
develop careers.
Yeah, so that's the purpose for this public lecture. So let me see if there are any questions. While people are thinking, I wanted to ask this question to Dr. Solanki also.
Yeah.
We are talking about lots of solvation, and you say that chemical engineers, they need to understand that solvation. I mean, what are the basic application? Why people are so worried about these processes? They try to mix the various solvents, and they try to study those properties.
No, solvent extraction is a very important process. How from plants you get many things that you want. Okay. So normal solvent extraction at normal temperature is not going to be very good. You cannot extract. Whereas when you go to supercritical extraction, you can really do wonderful things. Like supercritical CO2, it is used as a solvent. You need to separate also. In all processes, separation and association are the key things. So you will have to use solvent, mixed solvents. So your solvent is a tool now. Solvent is a tool for all these separation techniques. So
Right, I see.
all industry, chemical industry is all full of your solvation processes.
Right. The solvation is used for extraction, and then you separate them to the separation.
And many reactions occur in mixed solvents better than in pure solvents.
Yes, right. That is also.
So it gives you a medium, choose an appropriate medium for your reactivity.
Reactive. Yes, that's important.
And not only that, why we got interested, why should we study sodium chloride in DMSO water mixture? A person who was doing synthesis, he added just a pinch of salt to his reaction, the product increased 100 times. So, even things like ions, they really assist in your reaction, because if you see the real cell in our body, so many ions are there. It's a very complex system and so many reactions occur. We create proteins regularly with such accuracy. So many things are helping there. So, and it is 70% water, even in the cell. In our cell, it is 70% water. So many other mixtures are there. So reality is a very complex process. So we are only making a small part of reality and trying to predict what is going to happen.
Right. You showed us that though we know the three phases, but there really could be different other phases with water.
Correct.
Right. So I heard about these green solvents. Can you please briefly make a brief comment on that? What are those green solvents?
See, you don't want many chemicals to go into your water stream, correct?
Right.
So you don't want chloride to go into water stream, correct?
Right.
Even CO2 is all right. You can use CO2 as long as you can extract back. See, green solvent, you don't add any environmentally harmful thing to your nature.
Right. Okay. So after the extraction, only those parts should go, which is released, which is not harmful to the nature.
That's right.
I see. I have one more naive question from those fullerenes and fullerols.
Yeah.
We had C60 as the fullerene, and we added the hydroxyl groups.
Right.
We kept on adding until OH12, right? 12 hydroxyl groups.
Correct.
So should not we treat that as an impurity now? How many groups we can add without losing those properties of fullerenes? Chemical
You can almost add up to 44 they have added.
Okay, without
60
losing.
carbons are there, 60 carbons are there. Okay.
Right.
The reproducibility, see, when you add so many OHs, there will be mixtures of say 12 OH and 14 OH. It becomes very difficult to separate.
Right.
Okay, so that is the one challenge, because they will all have very similar properties, no? So to separate 44 OH from 42, again, it's a very complicated process. So they will say either small number of OHs or large number of OHs, and adding these OHs makes them more soluble. That is the reason. C60 is not soluble in water.
Right.
By adding these OHs, I can dissolve and I can use it as a species to carry drugs in the molecule. See, there are many drug carriers. That carrier should take it to the site I want and then break up.
Right.
It is almost like a capsule, although C60 is a very small capsule, right? Suppose I want to take a radioactive object and then the thing should break. As an example. Or something which is very harmful in the bloodstream. So I want it to go only up to the tissue where it should go and then split and act on that tissue.
Right.
All carrier molecules. So that is the reason for interest here.
Right. I know people might be waiting for a question, but I will ask one more small question.
Yeah.
You talked about the mix of solvents, water plus, I think it was methanol.
Methanol, DMSO, ether, many options. Dimethyl formamide, that is also a good solvent.
And you said that there is now competition between the two different atoms,
Correct. Yeah.
Right. So shall we say that it's a dynamic equilibrium or it's a non-equilibrium? What we should call it?
No, if it is no, things are always moving from inside and outside. So equilibrium is never going to be static.
Yeah, but there could be stable equilibrium, unstable equilibrium.
Yeah. So the main thing is whenever you have charged objects like ions or dipoles, water tends to dominate the first solvation shell.
Okay.
Whereas if it is an uncharged object, the non-aqueous solvent will dominate.
Right. Okay, because water has this electrolytic property.
Right. It has even the dielectric constant is very large, no?
Right.
So it allows water molecules to go very near the ions because of the large dielectric constant.
Mm-hmm. Thank you, sir. Yeah. So, questions from participants, other participants.
Sir, can you hear me?
Yeah.
Sir, I have one question. In ab initio molecular dynamics, you use two names, Born-Oppenheimer and Carr-Parellini,
Right.
CTMD.
Yeah.
So, can you elaborate that more?
See, the Carr-Parellini dominates using the density functional theory. It's all based on a density functional theory. The calculations are much faster.
Okay.
If you do your regular ab initio solving with the wave function, that is a much more challenging calculation.
Okay.
So Kohn-Sham model density function, that is much faster. So Carr-Parellini came earlier, but nowadays they want to do ab initio using the full wave function also.
Okay. Thank you, sir.
Okay, so we need to calculate the wave function every time and then calculate the energy and find the force.
Right.
Yeah, that will be very expensive.
Correct. So density functional is better because ground state, the density can give you much faster calculations. Because you don't calculate exchange integrals, there is a exchange potential that is used in density functional theory. So that makes it faster.
Okay.
100 times faster than your ab initio.
Oh. Thank you.
Right. Any other questions?
Sir, I had a question.
Sure.
Yes.
Hello. Sir, as you said that this fullerene can be used as a drug carrier. So how do you put some drugs inside it and release it on particular distance?
It's a model calculation. Fullerene, the diameter is only about 6-7 angstrom. You cannot put too many things inside. You can only put a small thing. Then you have to do with a larger one, say C100, C200 like that. Then it becomes easier. It's a model for drug carriers. Because you have to open the stitches and put like a tailor, no? Almost like a tailor, you have to open the bond and put inside and close the bond. Okay. So this is the model calculation for drug carriers, not the actual one.
Okay, sir.
Because at the most one methane or ethane, at the most a small molecule will go in that. The drug is going to be very large, no?
Okay, if there are no more questions, then let us thank Professor Tembe for taking his precious time to make us aware about the very, very useful and the topic which we generally do not come across, the computational chemistry. Thank you so much, sir. We will definitely look into some of the references you have suggested.
Yeah. Thank you. Good night and good night to all of you. Thank you for listening.